Okay. All right. Well, let us continue. This is where we ended up yesterday, and congratulations. This is the end of the second week. So we've gone through a number of chapters, and hopefully you're keeping up with the homework and what other videos you need to use to help you out. So anyway, let us continue. We were talking about the periodic table, and then how different groups had different names. So we had group 1A had their own specific name. They were called the alkaline metals. So in this question here, they're asking you, okay, can you name an alkali metal in the third period? So basically you find the alkali metals, which is in group 1, and then the third period, which would have to be sodium. Okay. Now the ones in group 7, right next to the noble gases, those had their own little name. That's the fluorine, the chlorine, the bromine, and the iodine. They were called halogens. Okay, so you go over to the halogen section of group 7A, and they're asking you, okay, name an halogen in the second period. Well, that would have to be the only one that's in the second period that's a halogen would be fluorine. Okay. Then finally, the last question, the noble gases. Noble gases are, oh, there we go. We got one more. Noble gases are in the group 8, okay? And they're asking you to name a noble gas, or at least give the symbol, in the fourth period. And so we just count down the periods, and that becomes krypton, okay? So, like I said, in the periodic tables, only certain groups have special names, so you want to be familiar with those special names. All right. Now, it's very crucial, important, I should say, to recognize the elements that are metals, nonmetals, and metalloids. Metalloids, if you recall, are the semi-metals. Why is that? Because in the next chapter, by recognizing what the elements are that come together to form a compound, will tell us what type of compound they are. And there's only 2 types of compounds. Of all the combinations that you can possibly have, there's only 2 types of compounds that are made, and those are ionic compounds and covalent compounds. And we're going to distinguish them between whether the ones that come together are metals and nonmetals. Okay, and that'll help us out a lot, quite a bit, to classify the different compounds. So refresh your memory as to which elements are the metals, which elements are the nonmetals. And if you forget, look at the this area here that's dark and starting with boron. If you go diagonally across, and then you come straight down, and then make a straight down to, and then shoot across to arsenic, and then straight down, and then across, straight down, and then across. Okay, forms a little stair step. Those there that are highlighted are the metalloids. Okay, so everything to the left of those metalloids are metals. Okay, so they're the ones in the darker kind of light blue colors. And everything to the right are nonmetals. Don't forget the other nonmetal over here, hydrogen. We put it there because it has 1 valence electron. That's why it's in group 1, excuse me. Okay, but it's not a metal. Okay, notice its color. And so if you think about it, there are 1, 2, 3, 4, 5, 6, 7, 8 metalloids. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 nonmetals. Okay, and the rest of them are metals. All right, so be familiar with that because that will help you out quite a bit in the next chapter. You classify the type of compounds that we work with. Okay, so um, the radius. We're still talking about the periodic table. We had one property that I introduced to you. That is that as we go down the periodic table, the elements get bigger. It makes sense, right? Because the electrons occupy a higher energy level, so the elements get bigger. Meaning the radius, that is the distance from the nucleus to the outermost electron, gets larger as we go down the periodic table. Okay. And so if we were to, for example, compare the size of, let's say, compare the size of, let's pick lithium versus potassium. Okay. Well, you can see potassium is in the fourth period. So it's a very big element compared to lithium. And so potassium is much bigger, it has a larger radius. So going down the periodic table, the radius increases, and hence the elements get bigger. Okay. Now, uh, that's pretty self-explanatory. Now, that's pretty intuitive. Go down the periodic table, bigger, larger energy level, the elements get bigger. But when we go from left to right, okay, or in this case, from right to left, the radius gets bigger. It's kind of counterintuitive, meaning that, let's go back to the periodic table. As we go down the periodic table, the radius gets bigger. Okay. But when we go across the periodic table, they get smaller. So if you compare lithium number 3 to, say, neon number 10, neon is much smaller. You might ask yourself, well, why is that? Okay, it's kind of counterintuitive. Well, let me explain. Okay, because as we go across the periodic table from left to right, what's increasing? We are increasing the number of protons, right? And we're increasing the number of electrons. And so there are more electrons and more protons, and that force that brings them together, because positive and negative, they want to attract to each other. Okay. And they pull the electrons in. And so going to from left to right, the radius decreases. Because if we look at lithium number 3, it has 3 protons, 3 electrons. Okay. And when we compare it with neon number 10, neon has 10 protons and 10 electrons. So there's a lot more force pulling the electrons and the protons together. So I've been asked the question, well, why don't they collapse onto each other? It's a good thing they don't. That's where the neutrons come into play. They kind of help counter that force. You don't want the positive and the negatives to come together. It'd be pretty messy. But the neutrons that are in the nucleus kind of counter that force, keeping the electrons away from collapsing. Okay, so going down the periodic table, the radius gets bigger. From left to right, the radius gets smaller because you increase the number of protons and electrons, and you increase the force of attraction. Okay, let's go back to the slide. All right, so this snowman kind of helps you give you the trend where the head of the snowman represents a radius, and then the bottom part of the snowman represents another radius. So you can see going on the periodic table, the radius gets bigger. So take that snowman and tilt it to, knock it down, And you can see that from going from left to right, the radius gets smaller. So that snowman kind of helps you out to help you remember the trend as to how the radius changes. Now, again, the reason they get smaller as you go across the table is because you increase the force of the protons and the electrons. And the electrons are pulled in closer together. Okay, there's a picture here to kind of give you a general trend. As always, and nothing's 100%, and so the radius does hop around in certain places, but in general, you can see that from going from left to right, the radius gets smaller, and from going from top to bottom, the radius of the atoms get bigger. Okay, so you might ask the question, which is larger, oxygen, selenium, or beryllium? Okay, well, to answer that question, we need the periodic table, and so we gotta find them. All right, so let's find them. Okay, oxygen. Oh, go down. Where'd it go? Oxygen's right here. Se is right there, and Te is right there. Okay, you can see there that Te is it's in the 1, 2, 3, 4, 5th energy level. So obviously that's bigger, and oxygen would be much smaller. Okay, so to answer that question, Te is much bigger. All right. Well, what about magnesium, sulfur, and silicon? Well, let's find them. Magnesium, sulfur, and silicon. Here's magnesium right there. Silicon. And what was the other one? Sulfur, I believe. Okay. When I share my files, I can't see the other file. I don't know where it went to. Yeah, it was sulfur. There it is. Disappeared. There we go. All right, so we got magnesium number 12, silicon number 14, and sulfur number 16. And they're going across the periodic table. They're in the same period, okay? So they're the same energy level. But as we go from 12 to 16, we increase the number of protons by 4, and we increase the number of electrons by 4. And so there's more forces between the protons and electrons, resulting in sulfur being smaller. Okay. Sulfur is smaller. And this, but the question was larger. So, okay, obviously magnesium is a larger one. Sulfur is smaller, again, because the protons and electrons are pulling each other closer in. Now, there are some videos about atomic size on the website. So, yeah, make sure you watch them. Okay. Now, we got a different property here. This is called ionization energy. Okay, let's break that word down. Ion. We're making an ion. Okay. In other words, to make an ion, I said earlier that either we're going to gain electrons or lose electrons. In this particular case, we're going to lose an electron. It's denoted there by the reaction. This is how we write reactions here. Okay, we have sodium, the element sodium. We're going to hit it with energy, and we're going to knock off one of the electrons. And so that arrow is the reaction. So sodium, elemental sodium, loses an electron to form an ion, and we kick off an electron. Okay, so ionization energy is the amount of energy necessary to remove an electron, the key word, from a neutral atom, from an element. We're going to talk about another property down the road here in a bit called EN, electronegativity. Has nothing to do, that property has nothing to do with removing an electron. So let's not try to confuse the two. So ionization is the amount of energy necessary to remove an electron from a neutral atom. Okay? So here in that equation, you can see that sodium elemental, an element sodium, releases an electron. Okay? Now, the trend is the IE, ionization energy, increases up a group. It's easier to remove an electron from a larger atom. Okay? So let's think about that for a second. Let's go back to the periodic table. IE, ionization energy, is greater when we go up the periodic table within the group. Okay? And so if we compare lithium to, say, potassium, it's going to be a lot easier to remove an electron from potassium than from lithium. Now, think about this for a second. Which is bigger, lithium or potassium? Okay. Well, based on the trend we just talked about, potassium is a bigger element. Okay. Now, what is it that they both have in common? They both have one valence electron. So both of them have one little electron. Lithium has it in the second period, and potassium has that lone electron in the fourth energy level, or the fourth period. And so potassium's potassium's electron is further away. Okay. And so its interaction with the nucleus is much less, simply because it's further away than lithium. And so it doesn't hold on to that electron, potassium that is, as tightly as lithium does, because lithium's lone electron is closer in. Okay. So it makes sense that if we hit it with some energy to remove that electron, it's going to take more energy to remove the electron from lithium than it would from potassium, because that electron is closer to the nucleus, and it would be harder to remove it. There's more force involved there. Okay, so that's what they're telling you there. Easier to remove electrons from a larger atom, simply because the electron's much further away. All right. Now, when we look from left to right, the ionization energy increases. Okay. And why is that? Yesterday, or could have been the day before, I said, put this in long-term memory. All metals want to lose electrons. Okay. And then I also stated that all nonmetals want to gain electrons, because again, the nonmetals are very close to the noble gas. They only need 3, 2, or 1 more electron to fulfill the octet. Okay. And so for them, it's easier to gain the electron than it is to lose it. Whereas metals, just by default, they rather just give them up. And so as you go across the periodic table, remember from where we had metals, nonmetals, and metalloids, the whole left side is made up of metals. So when we go from left to right, the ionization energy increases, because now we start getting into the metal, non-metal section, and they want to hold on to the electrons tightly. And yes, we can get an electron off, but they're going to hold on to what they have much tighter than the metals themselves. Okay, so our trend is from left to right. Ionization energy increases, and ionization energy increases as we go up the periodic table. Okay. Now, if we were to graph that information, you get a graph that looks like this. Okay, and you can see that hopefully that the general trend, it looks a little complicated here, but it really is. Okay, because here we start with the first one with hydrogen, and it's in the far left. It's got one valence electron, and then we go across the periodic table to helium, and the ionization energy gets much greater as we go from left to right. As we start again, we go around the horn, and we start off with lithium right here, and we go across the periodic table all the way to neon across the periodic table. And so we go lithium, which is a metal, and the energy required to get an electron off, let's say neon on the other side, is much greater. So the general trend is as we wrap around the periodic table, here's the first period, second period, this is the third period. Eventually we get to the fourth period, and that hill is not so steep. Now you might think, well, why is that? Well, because as we go down to the fourth, fifth, sixth, and the seventh period, the radius is much bigger. And so those electrons outside in the valence electrons, they're not interacting very tightly with the nucleus. So yes, the trend still is greater as you go from left to right, but the total amount, eventually that line will flatten out. Okay. So this is what this graph shows. Let me get rid of this stuff. Now let me ask you, do a compare and contrast. Which element has a higher or larger IE, ionization energy? Chlorine, aluminum, or magnesium? Okay, you don't have to look at the periodic table to answer this question. You just have to recognize one thing. Of those three, do we have any nonmetals there? Is chlorine a metal or a nonmetal? What do you guys think? Exactly. Chlorine is a nonmetal. And if we compare aluminum, which is a metal, magnesium is a metal, and they're going to lose electrons very easily with no problem. So the nonmetal automatically is going to require higher energy. Okay. And so we don't have to even look at the periodic table. We first look at the elements we're being asked the question about. And if we only have one nonmetal there, that's the one that's going to have the larger IE. Okay, now we look at these. We got lithium, rubidium, and potassium. All of them are metals. Okay, so to answer this question, we have to figure out where they're at on the periodic table. And so let's find them. Okay, and here they are. We got lithium right there, rubidium, and potassium. Oh, and potassium right there. Okay, so they're all metals. They all happen to be in the same period. And so to answer this question, it's a matter of which is bigger. RB is a bigger element. So it's and they all have in common because they're in group one, they all have one valence electron. Okay. So, but for RB, that valence electron is in the fifth energy level? 1, 2, 3, 4, 5. Fifth energy level compared to lithium, whose its one valence electron is in the second energy level. And so RB's valence electron is way out there, so it doesn't interact very tightly with the nucleus and the protons. So it's going to give that up much more readily than lithium will. Okay. So Li being the smaller is going to hold on, the smaller element is going to want to hold on to its electron much tighter than Rb. Okay, also on the course website, there'll be other videos with concerning ionization energy. So, feel free to jump in there and take a look at them. Okay, which brings us to the second property we're going to talk about. Okay, this is En, electronegativity. Okay, now IE was just a single element itself, a single neutral element, trying to figure out how much energy it took to remove an electron. With respect to electronegativity, this is the attraction of electrons in a bond. When chemicals make a bond, okay, they will take an electron from one, for example, and an electron from another, come together and form a bond. Okay. And what happens normally, not normally, but one or two things can happen. That those two electrons that were being shared are going to be shared equally or unequally. Okay, they're not going to break the bond. They're sharing this. These electrons are being shared between two different elements, and they're going to be shared either equally, or one of them is going to pull the electron density further to itself. Okay, so and this is what it is a measure of. It is called electronegativity, and that is the affinity or the ability to pull the electrons onto itself. Now, every element has an electronegativity value. We're not asking you to memorize all the values. All you got to remember one thing: fluorine. Fluorine is the most electronegative element that there is. Okay, and so fluorine's right here. Okay, and so that being the most electronegative, that means the trend of electronegativity from going from left to right is increases, and going from the bottom to the top of the product table, electronegativity increases. Okay, so all we can do is compare and contrast. If we were to compare, for example, um, the electronegativity of, let's say, nitrogen and carbon, to ask the question, which is more electronegative, who has a higher electronegativity, carbon or nitrogen, all we can say is this. One, find their position relative to fluorine. Find which one is closer to fluorine. Nitrogen is closer to fluorine. Therefore, nitrogen is a lot more electronegative than carbon. Okay? So if there was a bond between carbon and nitrogen, a specific bond where they're sharing electrons, then nitrogen would have a tendency to pull the electron density onto itself much more than carbon does. Very important property. It has a big effect on a lot of things in chemistry, electronegativity. And we're going to see more and more of that as we proceed. So this property is something that get a hold of, because we're going to use it quite a lot in the later chapters. Okay. All right. So again, noble gases, obviously they don't have any electronegativity at all, simply because their octet is full, and they don't make bonds, and they don't do it for Chem 130. They don't react. They don't do anything. So no electronegativity. Okay. So um, Remember the trend left to right increases, En, and bottom to top electronegativity increases. Okay, that being said, do take a look at those chapters, those videos on that, uh, on electronegativity, ionization energy. Okay, let me do something else. There is, let me stop to share, on our website. Okay, let me find it. In the modules, in the very bottom, there is a build an atom additional resource. Okay, and let me start to share here. Where'd it go? There it is. Hopefully you can see that. Let me back it up so I can show you where it is again. If you click the modules as you enter our course website, Canvas website, go all the way down to additional resources, and there's this one called Build an Atom. Click it, and it brings you to this. It's a simulation. Okay, go ahead and select the atom, the first selection there. And what this does is kind of, we had the previous chapter that we talked about protons, neutrons, and electrons. And this will kind of help you out to get a better picture on things. For example, if I were, you can just grab a proton, grab it, and bring it into the center. See, the moment I put in a proton into the atom here, the dotted spheres represent the energy levels. Guess what? I made hydrogen. Remember, the proton defines the element. So if I continue to add protons, I'm making the different elements. Okay. So let's take some off. Okay. Now we got hydrogen. Now if I grab a neutron, excuse me, an electron, if I put it on the outside dotted line circle, guess what? It goes on the inside because this is the first energy level, the 1s1. Okay. Look at our net charge. For example, let me take that electron off. The net charge is a +1, right? Because there's no electrons. The proton has a +1. The moment we put an electron in, now we have a neutral element. Okay. Neutral element. Now the neutrons, they make the isotopes. And so we can put in neutrons in there and we create an isotope because now it has one proton, one electron, and one neutron. Okay. Which is stable. And then hydrogen does have a third isotope with 2 neutrons, but it's a little bit unstable. If you click the stable button, you see it bouncing around. Okay, let's do this. Let's fill her up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Fluorine. We're going to make fluorine. Okay. Now we're going to put in some neutrons until we get it stable. Fluorine, for example, has 9 protons, 9 electrons, and it should be 11 neutrons. One more. There's our most stable or the most common isotope. Okay. Now we're going to add electrons because fluorine has its atomic number is 9. Okay, so I've added 1 already. Our net charge is a +8 because we got 8 protons in there and 1 electron. Okay, notice where that electron went to. I'm gonna have another one, add another one here. I'm gonna slide into the innermost, but it won't fill it. It comes out to the outermost, okay? Because now it's in the 2s orbital, and now I keep filling up because fluorine should have 9 electrons for neutral fluorine. And one more. Okay. Now, fluorine is in group 7. How many valence electrons does it have? 7 on the outermost shell. 2 of them in the s orbit and 5 of them in the p orbit. But there's a total of 7. It has room for one more. It's a nonmetal. I mentioned earlier that it will gain electrons because it's a nonmetal. Right now in this state, it's neutral charge, because it has an equal number of protons and an equal number of electrons. The moment I add one more electron, now it becomes an ion and it has a negative charge. Okay. Why? Because it has room for one more electron now. Now the octet is fulfilled and is isoelectronic to neon. So anyway, this little simulation will help you out to understand how the neutrons and protons and the electrons are all interrelated, okay, and help you to understand how you get charges. Unfortunately, you can only go to one more, which is neon, okay? And there's neon. By adding one proton, we created neon, okay? And here's a mass number, always an equal number, a whole number. Okay. Um, any questions right now? No? Okay. Well, I tell you what, I'm gonna stop it here. I'm gonna stop it here. And don't forget, we have your next quiz is on Monday, covering these last 3 chapters. So uh, I'll be here tomorrow for office hours if you have any questions. So feel free to stop by. Okay. All right. You have any questions, Luria? Did I pronounce that correctly? Okay. 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 All right. Well, uh, thank you. And I'll see you next week. Or if you have questions, feel free to stop by during my office time.